33. So in 33 we have a circuit that looks like so. Boop, 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 boop. Swoop, boop, boop. Boop, 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 boop. So in here we have some batteries. So this is 1.4 ohms, this is 1.6 ohms, this is 16 volts, that's the plus side, that's the minus side. This one is 8 volts, that's the plus side, that's the minus side. This one is 9 ohms, this one is 5 ohms, this is point A, this is point B. Okay, so the circuit shown contains 2 batteries, so it's these little rectangles here. So in each battery, you have your EMF, which is this dude producing your voltage push, and some internal resistance. And we have 2 resistors just by themselves. So we want to find the current in the circuit, the magnitude and the direction, and we also want to find the terminal voltage, so like what you would actually measure if you hooked up your battery to a voltmeter, between here and here. So because we have 2 batteries in here and they're facing opposite directions, we're going to want to do Kirchhoff's laws. So this is a super little baby example of Kirchhoff's laws. So the first thing you want to do for these guys, we're going to get some colors out, is draw the direction of the current. It doesn't have to be the actual direction of the current, you're just defining your current for here. So here's my big fat battery. I like him better, so I'm going to say my current is going this way. Boop, 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 boop. So this is I. So now because we only have one loop to go around, we don't have to give them little separate labels. We can just call it I instead of like I1, I2. So when we get harder circuits, that'll become more important. Okay, so now we have our current going through. So with Kirchhoff's loop rule is the one that we want to do. Loop rule, because we don't have any junctions because there's no splits in our current. So we start at a spot. So I'm going to start here on this side of the 16 volt EMF. So when you do your loop, you follow all the way around. So the direction that we go through our loop actually doesn't matter. But I'm going to follow the current because that's the way I drew it. So when we go through a battery, if the current is going through the battery the way that it's supposed to, it's a plus. So then we follow through the resistor, and if we're going through the resistor the same direction that we drew the current, that's a minus. Minus IR. So now I go through here. Now I'm going through this resistor the same direction as my current. So that's a minus current times 5 ohms. Going through this resistor the same direction as my current. So that's a minus I 1.4 ohms. So now I'm going through this battery backwards. I'm going from plus to minus instead of minus to plus. So instead of adding this battery, I'm subtracting this battery. So then I come down through this one. I'm going through this resistor in the same direction as my current. So that's minus IR. And I'm back to where I started. So that entire loop has to equal 0. So now I can collect all my things. So I have 16 volts minus 8 volts. So that's 8 volts. Then I have minus I 1.6 plus 5 plus 1.4 plus 9, because I pulled all my minus signs out here, is equal to 0. So that's 8 volts minus I 1.6 plus 1.4 is 3. 12, 17. So if I move that to the other side, I get 8 volts equals 17 ohms times I. So I is 8 volts over 17 ohms. So 8 divided by 17 is 0.47 amps. And that's how you get your current. So the next part wants us to find what is the terminal voltage between point A and point B. So we know that we have 16 volts from this EMF, but then we're also losing a little bit through this guy. So we know the current through this resistor. So from Ohm's law, V equals IR. The voltage that that resistor is slurping out is the current, 0.47 amps, times that resistance, 1.6 ohms. Which is 0.75 volts. So my terminal voltage is 16 volts that I gain, and then I lose 0.75 volts because I'm going through this resistor the same direction as the current. So that's going to be 15.25 volts. Because resistors suck out voltage. That's what they do. So, oh, I almost forgot. So through here, because we ended up getting a positive answer for our current, that means that the direction that I drew this current was correct. So had I drawn my current going the other way and followed my loop that way, I would have gotten a negative answer. So when you get a negative current, it just means that it's going the opposite direction of how you defined it. So that's why it doesn't matter which way you draw your loop. So this is going counterclockwise. Counterclockwise. And that's it.